All right, physicists. Well, today I'd intended to go over Gauss's law, but in fact, this video is just going to be more more review about electric fields. Now, next week we are going to do Gauss's law. Gauss's law is the idea that we can relate the flux through a surface surrounding a charge to the electric field. Now, the flux is the sort of funny thing because you associate each little piece of a surface with an arrow. Okay, so like here, I would have the area be of that little square be represented by an arrow proportional to the area of the surface, and then the flux would be the dot product of the electric field piercing that surface. So if the electric field's in this direction, I have some angle. It would have to be proportional to, the size of E times the size of A times the cosine of the angle between the two. And so essentially you're going to add up all the little fluxes from your surface and relate that to the charge that is enclosed inside of that surface. And that doesn't seem super useful, but it turns out that that law makes it very easy to calculate the electric fields for certain charge distributions. Now, today I'm not actually going to do that for you because I realize now we actually have a break after this video. We've got Labor Day coming up. So instead, I just want to make sure we're solid on electric fields, solid on dipoles, and then we're going to push off our Gauss's law till next week. So what have we been doing this week? We have been associating forces and fields. So if I have an electric field, I put a charge in it, this charge will experience a force. An electric field is a vector quantity. A force is also a vector quantity. That means it has a direction and a magnitude. And if the charge is positive, the force will have the same direction as the electric field. On the other hand, if the charge is negative, the force will have the opposite direction. Now, the electric field contribution points out from a positive charge in towards a negative charge. This is because we think of the electric field as telling us something about the force that a positive charge would experience. So that's a convention. Of course, from this electric field, we could, if we stick this back in and get the force, we could get our Coulomb's law back out of that. Now, we've been talking this week about a number of different electric fields that result from different charge distributions. One of the most significant ones for us to think about is that of a little dipole. Now, a dipole is a charge distribution where you have a positive charge and a negative charge that are close to each other. And because they're close to each other, the total charge of that thing is zero, and at far enough distances, the electric field should die off. And as we find out, the electric field does die off more quickly than for our point charge. So instead of dying off as 1 over r squared, it dies off as 1 over r cubed. And the thing that tells us how big the magnitude of that field is, it depends on the product of how big these charges are and their displacement. So it doesn't depend on either one individually, but it depends on their product. Now we have a plus charge and a minus charge. Above and below, the electric field is pointing with the dipole, but because the electric field points from plus to minus, our electric field is pointing opposite those charges between the two. Okay, so on the sides it's pointing opposite, along the dipole axis it's pointing with. Now, we're going to do a number of different practice problems to get ourselves ready for the quiz for this week, and to make sure that we're feeling strong with this electric field business. So here's a question. It's to help us practice with the electric field of a point charge. It says, at a distance of 1 centimeter from an electron, the electric field strength has a value of E. At what distance is the electric field strength equal to E over 10? Okay, so if I have an electron 1 centimeter away from that, we're going to have K. K is, of course, another name for 1 over 4 pi epsilon naught. K E over R squared, that would be my electron charge, or really I should put in 1 centimeter squared. That's the value of E. E, of course, is that 1.602 times 10 to the minus 19th coulombs. K also has a value 8.99 times 10 to the 9th Newton meters squared over coulomb squared. And it asks me, at what distance is the electric field strength equal to E over 10? So that would be 1/10 of Ke over 1 centimeter squared is equal to, and I want to solve for R. So I have not changed my charge. I'm just going to leave this as a variable. I don't know what it is. K and E are constants, and I can divide both sides by K and E. Now I notice that I can take the reciprocal of this and say now that R squared equals 10 centimeters squared. So if I want to solve that now, I can say R equals the square root of 10 centimeters. This is a typo on my part. Now 10, of course, the square root of 10 is going to be, well, if I take 3 squared, that's 9. If I take 4 squared, that's 16. So the square root of 10's got to be somewhere between 3 and 4. So let's pick our answer. That's between 3 and 4. And we're done. Okay, now, did I have any? Okay, no. I want us also to remind ourselves a little bit about how electric field lines give us information about electric charge and electric field magnitude. Electric field lines point in towards negative charges and point out of positive charges. The other thing to remember about electric field lines is that they're close together where the electric field is strong, and they're far apart where the electric field is weak. So here it says, consider the electric field lines shown in the drawing. Which of the following statements correctly describes this situation? Are they both positively charged, both negatively charged? Is one positive, one negative? Is one negative and the other positive? Okay, so let's look here. I have my electric field lines pointing in towards A, so that means A must be negative. They're also pointing in towards B, so B must be negative. Here I've got my lines, field lines closely packed together, so I would expect the field there to be strong, the field there to be strong, and as we go out far away from this, the field will get weaker. Okay, so A and B are both negatively charged, and we know that because they both have the field lines pointing in towards them. Now I'd like to do now 2 problems where we practice with adding electric fields as vectors. And these are qualitative problems, but I think it can be helpful. So in this problem it says we have 4 charges that are located on the corners of a square as shown in the drawing. What is the direction of the net electric field at this point labeled P? It's not labeled P in our drawing, but you can imagine with me. Now the electric field contribution of a point charge points in towards minus charges, out from positive charges, and it's related to the charge, and it's related to the distance. So the distance of this point is equal from all of these four charges. The four charges each have an equal magnitude, and so if I label them 1, 2, 3, and 4, I can draw in my electric field contribution from each. This one's going to be pointing out away from 1. So there's my electric field contribution from 1. My contribution from 2 is going to be pointing in towards 2 because it's minus. My contribution from 4 is going to be pointing away from 4. And my contribution from 3 is going to be pointing toward 3. So I hope you can see that these are all going to cancel out. There's no direction. The electric field at point P is 0 newtons per coulomb. And it's because E4 is opposite the direction of E1 and has the same magnitude. So these two cancel, and those two also cancel. And you'll remember we did a problem earlier this week where I was just cavalierly crossing these off if they had the same magnitude of charge and were equidistant from a point. The electric field contributions from those we know will just cancel. Okay, so that's one. Now, again, let's think a little more carefully. Remember, our E is related to KQ over R squared. Here's another example now where we don't have the same charges, the same magnitude of charge. They are still equally distant. So I have 1, 2, 3, and 4. So let's draw in our electric field contributions again for this slightly different problem. Now in this case, this is going to be a big contribution because it has a bigger magnitude. So there's my E1. My E2, on the other hand, has a smaller charge, so it's going to have half as big a magnitude. Okay, so there's my E2. Magnitude is half as big as E1. It's pointing towards E2. E3 is also going to have a big magnitude because it has a bigger charge. So the electric field vector is going to be pointing towards. So there's my E3. And then my E4 is going to be pointing away. Okay, so now if I wanted to add these all together, my E2 plus my E4 would look like that. My E3 plus E4 would give me a vector pointing down. And so overall, my total vector is going to be somewhere pointing, so my 3 plus 4 is going to be pointing straight down. My 4 plus, or sorry, oh yeah, my 3 plus 1 would be pointing down. And so if I have my 1 plus 2 plus 3 plus 4, it's going to have a slightly lesser magnitude than if I just added my E3 plus my E1, but it's still going to be pointing toward the middle of the bottom side of the square. Okay, let's just do not many more. This one has us ask the question, where would we be experiencing the largest force with a charge if I put it in this electric field? Well, would it be A, B, C, D, or E? Where would my test charge experience the largest force? It would be D, because that's where the electric field lines are closest together. And then we're back to where we were in our last video. All right, so I know that people have a little bit of trouble with electric dipoles. It's just it's a little bit tricky to think about. So let's review this again. Remember, an electric dipole is a minus charge and a plus charge that are separated by a distance d. We consider the electric dipole moment to be a vector. It's a vector where it's pointing from the minus charge to the plus charge. There's that p vector. In this case, the P would be pointing up like this. Okay, so P is pointing from minus to plus. It is a vector. It does have a magnitude of Q times D. So this is Q in coulombs, D is in meters. So your overall units on your dipole moment are coulombs times meters. Now, because electric fields, this is the same slide I showed in the last video, but you have a plus charge and a minus charge. If you put charges in a electric field, because the overall charge is 0, the overall force is going to be 0, but it experiences a torque. And because we have our U equals, the integral of that torque over an angle, you're going to end up with a potential energy. So I want to just draw out something to help you picture this. So if we have our E pointing in some constant direction, there's our electric field. I could have my dipole oriented along. So there's my minus to my plus, there's my P. So in this case, I would have my angle between the dipole and the electric field as 0. I could have my angle as 90 degrees. So here I have my minus and my plus. There's my dipole. Or I could have my angle as 180 degrees. So in this case, I would have my plus and my minus, and so my dipole moment would be pointing the opposite direction as my field. Okay, so here I have my field pointing in my plus x direction to the right, and I have 3 different possible orientations that I want to think about. Now, let's first think about the torque in each one of these orientations. Now, the force on my plus is going to be pointing with the field. My force on my minus is going to be pointing opposite the field. So this is my P, this is my P, this is my P. Now, the torque is, of course, telling you about how much of the force is perpendicular to the direction of your axis of rotation. So here my torque would just be 0 newtons times meters. On the other hand, here I would get a big torque because my force and my axis of rotation for that are pointing in perpendicular directions. So here I would have a torque of P times E, and then here I would have, it's a little hard to see, but there's my force pulling on my plus and my force pulling on my minus. Now here the pointer is such that this is going at the angle equals 0, you're going to have a stable equilibrium. At 180, you're going to have an unstable equilibrium, such that any little push out of that is going to get this starting to spin. Your dipole wants to align with the electric field, so this torque here would be 0 newtons per newton meters as well. So there's our torques. Now, what about the energy, the potential energy? Now, you may or may not know this, but physicists cannot measure energy. We can measure differences in energy, but not energy. And so I'm going to put this as 0 joules, but that doesn't mean much. It just means I want to call that 0 joules. I could have less energy than that or more energy than that. Now, the point which has the least potential energy is right here when the dipole is oriented right along the field. Okay, so it's going to be lower than that 0 joules. It's going to be minus P times E. Remember, P is the the magnitude of P is going to be the magnitude of the charge times the distance. So this is going to have units of charge times distance times newtons over charge gives you units of energy. Remember, it's a little tricky to think about, but torque also has units of energy because it's force times distance. Okay, now I could also have a higher energy orientation, so that's when my dipole is oriented opposite the electric field. So there's your P times E. And overall, here the magnitude of the torque is going to go as P times E times cosine of theta. And here the potential energy is going to go as minus P times E. Whoops, this should be sine. And this should be minus P times E times cosine of theta. Okay, so theta is the direction between my E and my P. So there's the minus charge, the plus charge, and this is the angle that I'm talking about. So let's use this information. This is the problem that we did last time. It's in our last video, so I'm going to not repeat that. If you want to look at this problem, go to the end of the last video. I will help you out. This is actually one of the problems I assigned as a homework problem. It says an electric dipole consists of charges of plus 2e and minus 2e separated by 0.78 nanometers. Okay, so I've got my plus 2e and minus 2e, and this is 0.78 nanometers. So I already can calculate my dipole moment from this. It's going to be 2e, that's going to be my q, times this d. So that would be 2 times 1.602 times 10 to the minus 19th coulombs times the d is going to be 0.78. If I want to have nanometers, it's going to be times 10 to the minus 9th meters. Okay, so you can get a number out of that. And then it asks, calculate the magnitude of the torque on the dipole when the dipole moment is parallel to, perpendicular to, and anti-parallel to the electric field. Well, look back on these pictures that we've done. It's easy to know what the torque is when you're parallel or anti-parallel. In that case, the torque is just 0 and 0. On the other hand, when you're at perpendicular, so P and E are perpendicular, that's the case where the sine of 90 degrees is going to be 1. So for part B, the torque would be P times E. So we know what the P would be there. You get the numbers out, put them in. And then for your E, they also give you that as 3.4 times 10 to the 6 newtons per coulomb. And torque has units, as always, of force times distance. So it'd be Newton meters. If you put joules, I won't count you off. But okay. Now, this is the problem that students typically have the most difficulty with out of this homework set. So I will try to talk you through it. It says the potential energies associated with 4 orientations of an electric dipole and an electric field are these things. It asks you then to rank the orientations according to the angle between the electric dipole moment and the electric field, and then the magnitude of the torque on the electric dipole greatest first. Okay, so let's plot what these things look like. So here's our um, energy versus orientation, and then our torque versus our orientation. So our energy versus our orientation starts at some negative value, minus PE, when my dipole moment is totally aligned with the field, when P is pointing in the same direction as E. Goes to 0 by convention when we're at 90 degrees, or pi over 2. And then it goes to some positive value. Its highest potential energy is when we're at 180 degrees. On the other hand, the torque is 0 when I'm aligned or anti-aligned with the field. The torque has its biggest magnitude when my dipole is perpendicular. Okay, so it says you have a minus 5 u naught, minus 7 u naught, 3 u naught, and 5 u naught. So my minus 7 is the biggest magnitude of the potential energy. So let's put that, it's going to be somewhere here. So it's going to be, that's my minus 7 u naught, that's my 2. And then my minus 5 u naught is going to be a little bit less than that. So that's going to be my, it's a little hard to see on the drawing, but that's 2. This is going to be 1. I have if I go the same relative angle to the perpendicular over here, that's going to be my 5 u naught, so that's going to be my 4. And then 3 u naught is going to have a magnitude that's a little less, so that's going to be somewhere over here, 3. Okay, so over here I'm going to have the same ordering on the torque, 2, 1, 3, and then 4. So if I'm looking, ranking the orientations of the angle between the electric dipole moment and the electric field, and the magnitude of the torque on the electric dipole, and we start with the greatest, well, my greatest angle is going to be 4, where I have the closest to anti-aligned. It's going to be bigger than 3. It's going to be bigger than 1. It's going to be bigger than 2. So that's my part. That's my part A. And then my part B, I can look at how big these magnitudes on the torque are going to be. It appears that 3, which aligns with that, is going to be the biggest. And then 4 and 2 are going to be the same. And then 4 and 1 are going to be the same. That's the minus 5u and 5u. And then the one that is most closely to anti-aligned is going to be the smallest, or sorry, closest to align with the field. Okay, so it's all right if you think your way through it, but it is a little tricky to do that. Okay, so at the very end of last time, we talked a little bit how microwaves worked, where your electric field is flipping back and forth and back and forth and back and forth about 2.45 billion times per second. Some of that heat of flipping is transferred into heat when you have a hydrogen bond between a trio of oxygen or of water molecules, and so that can cause that energy from the poor alignment between the water molecules and the electric field in the microwave can be transferred into heat. Okay, so next time we're going to go ahead and talk about electric flux, give some examples of that, talk about Gauss's law, and do some of our greatest hits for Gauss's law. I don't think we need to do those today, though. We'll come to those in our next video. So have a nice break, and thank you for watching.